Welcome to Math Zone African Motives. In this tutorial, we will be solving a hydraulics question from a past paper, working step by step through each part. Our objective for this session is to calculate the effort required to lift a load using a hydraulic press and to determine the distance a load is raised after a number of pumping strokes. Let's begin with question 5.1. Question 5.1 reads, the data below refer to a single-acting hydraulic press. We are given four pieces of data. First, the diameter of the ram piston is 450 millimeters. Second, the diameter of the plunger piston is 100 millimeters. Third, the stroke length of the plunger is 120 millimeters. And fourth, the mechanical advantage of the plunger is 20. Our first task in part 5.1.1 is to calculate the effort that must be applied to the handle to lift a load of 4.6 megagrams. If the efficiency is 90%, let's list the known variables and convert them to the standard SI units to prevent errors in our calculations. The diameter of the ram, which we'll call D, is 450 millimeters. To convert this to meters, we divide by 1,000, which gives us 0.45 meters. The diameter of the plunger, which we'll call D, is 100 millimeters. This converts to 0.1 meters. The load to be lifted, or the mass, is 4.6 megagrams. A megagram is also known as a ton, which is 1,000 kilograms. So, 4.6 megagrams is 4,600 kilograms. The mechanical advantage of the plunger, MA, is 20. And finally, the efficiency, I, is 90%. Our goal is to find the effort, which we'll denote as E. First, let's determine the force of the load. We can calculate the weight of the load using the formula. Weight W equals mass times the acceleration due to gravity, G. We will use G as 9.8 meters per second squared. Substituting our values, the weight is 4,600 kilograms times 9.8 meters per second squared. This gives us a load force of 45,080 newtons. We've now converted the mass to a force. Now, let's find the force that the plunger must exert to lift this load before considering the mechanical advantage of the handle. For a hydraulic press, the ratio of the load force, F load, to the effort force at the plunger, FOP plunger, is equal to the ratio of the square of the ram diameter, D, to the square of the plunger diameter, D. We can rearrange this formula to solve for the plunger force, F plunger. The plunger force is the load force times the plunger diameter squared, divided by the ram diameter squared. This formula allows us to find the force at the small piston required to lift the large load. Plugging in our values, the plunger force is 45,080 newtons times 0.1 squared, divided by 0.45 squared. Calculating this gives us a plunger force of 2,026.173 newtons. This is the force needed at the plunger piston. Next, we will use the mechanical advantage of the handle. The mechanical advantage relates the plunger force to the effort at the end of the handle. The mechanical advantage, MA, is defined as the force the handle applies to the plunger, which we're calling the load at the plunger, LL plunger, divided by the effort applied to the end of the handle, E handle. The force we just calculated, 2,026.73 newtons, is this load L plunger. We need to find E handle. Rearranging the formula, the effort on the handle is the load on the plunger divided by the mechanical advantage. So it's 2,026.173 newtons divided by 20. This gives a theoretical effort of 111.309 newtons. This is the effort required in a perfect frictionless system. However, the problem states the efficiency is 90%. This means the actual effort we need to apply will be greater than the theoretical effort. Efficiency is the ratio of output power to input power, and it can be expressed as theoretical effort divided by actual effort. So, the actual effort, E actual, is the theoretical effort, E theoretical, divided by the efficiency, E. Note that to get the actual effort from the theoretical effort, we divide by the efficiency as a decimal, or multiply by the reciprocal of the efficiency. In this case, the efficiency is 90%, or 0.9. So, the actual effort is 111.309 newtons divided by 0.9, or multiplied by 100 over 90. This gives us a final answer of 123.677 newtons. This is the effort that must be applied to the handle. Comparing this to the provided memo, our answer matches perfectly. So, to recap, we converted all units to SI, calculated the load force, used the hydraulic press principle to find the plunger force, applied the mechanical advantage formula, and finally adjusted for the 90% efficiency. We have successfully solved part 5.1.1. This is just an example for illustration purposes. Next, let's tackle question 5.2. The question is, the plunger of a 3-cylinder pump has a diameter of 85 millimeters and a stroke length of 590 millimeters. The crankshaft speed is 250 revolutions per minute. Calculate the quantity of water delivered in liters per second if the slip is 1.7%. Let's first list our knowns and convert units to SI. We have 3 cylinders, so C equals 3. The diameter D is 85 millimeters, which is 0.085 meters. The stroke length SL is 590 millimeters, or 0.59 meters. The crankshaft speed N is 250 revolutions per minute. To convert this to revolutions per second, we divide by 60, getting 4.1267 revs per second. Finally, the slip is 1.7%. We'll use a standard formula for the theoretical volume delivered per second. The theoretical volume delivered, V theoretical, is the number of cylinders, C, times the area of one plunger, AIP, times the stroke length, SL, times the crankshaft speed, N. Since the area AIP is PAD squared over 4, we can expand the formula. So the theoretical volume is C times pi d squared over 4, all times SL and N. Plugging in our values. 3 cylinders. Diameter 0.085 meters, stroke length 0.59 meters, and speed 4.167 revolutions per second. This gives us a theoretical volume delivered of 0.0418 cubic meters per second. The question mentions slip. Slip is the percentage by which the actual volume delivered is less than the theoretical volume delivered. The relationship is that actual volume equals theoretical volume times 1 minus the slip percentage. The slip is 1.7%, or 0.017 as a decimal, so we multiply the theoretical volume by 0.017, which is 0.983. The actual volume delivered is 0.0411 cubic meters per second. Finally, we need to express this volume in liters per second. We know that 1 cubic meter is equal to 1,000 liters. To convert, we multiply our result in cubic meters per second by 1,000 liters per cubic meter. So, 0.0411 times 1,000 gives us 41.138 liters per second. We will round this to 3 decimal places. Comparing this with the memo's answer, it matches perfectly. So, we calculated the theoretical volume delivered, adjusted it for the given slip, and converted the final answer to the required units of liters per second. We have successfully solved part 5.2. Now for our final question, 5.3. The question states, the borehole pumps water from a depth of 70 meters at a rate of 320 liters per minute. The installation efficiency of the borehole pump is 80%. Determine the power of the driving pump of the electric motor. This question is about pump power. We need to find the input power of the motor, given the output power of the pump and the system's efficiency. Let's start with our given values. The height or depth, H, is 70 meters. The volumetric flow rate, Q, is 320 liters per minute. The efficiency, I, is 80%. We'll use a formula to calculate the power output of the pump. P out. This power is the rate at which the pump does work on the water. The formula is out equals the density of the fluid, R times the acceleration due to gravity, G times the height, H times the volumetric flow rate, Q. For water, the density V is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. We need to ensure all units are consistent. Our flow rate is in liters per minute, which is not standard SI. We must convert it to cubic meters per second. To do this, we multiply by the conversion factor for liters to cubic meters and divide by 60 to convert from minutes to seconds. This gives us a flow rate of approximately 0.053 cubic meters per second. Now we can substitute all our values into the power output formula. P out equals 1,000 times 9.8 times 70 times 0.05. Calculating this gives a power output of 3658.627 watts. Let's quickly check this against the memo. The memo calculated pressure, then volume, then power output. Their method is also correct. Their intermediate values are slightly different due to rounding in the volume calculation, but their final power output value of 3,658, 666, 438 watts is incorrect by a factor of 10 to the 6. It seems to be a typo or an error in units, as 3.66 kilowatts is a reasonable output power for a pump. Let's proceed with our calculated output power. Now we need to use the efficiency to find the input power. The formula for efficiency is output power divided by input power multiplied by 100. We want to find the input power, P in. Rearranging the formula, PIN equals P out divided by I multiplied by a 100. We are essentially dividing by the efficiency as a decimal. Plugging in our values, PIN equals 3658.627. Watts divided by 80 times 100. This calculation gives us an input power of 4573.284 watts. The memo gives an answer in kilowatts, so let's convert our answer. To convert from watts to kilowatts, we divide by 1,000. So the input power is 4.573 kilowatts. The memo's answer, after correcting the large number, is 4573.333 watts, or 4.573 kilowatts. Our answers match when considering the proper magnitude. To conclude part 5.3, we calculated the pump's power output using the depth, flow rate, and fluid properties. Then we used the system's efficiency to find the required input power from the electric motor. This completes the entire question. Let's quickly summarize what we've learned and accomplished in this tutorial. We started with a single-acting hydraulic press and learned how to calculate the effort required to lift a load, taking into account both the hydraulic advantage and the mechanical advantage of the handle, as well as the system's efficiency. Then we calculated the distance a load would be raised after multiple pumping strokes, understanding the conservation of volume principle and how to adjust for efficiency. In our second problem, we analyzed a 3-cylinder pump and determined the actual volume of water delivered per second, accounting for the effect of slip. And finally, we solved a problem about a borehole pump, calculating the power that the driving motor must supply to lift water from a certain depth at a given flow rate and efficiency. We also learned the importance of converting all measurements to standard SI units and of carefully interpreting and applying the formulas for efficiency and slip. If this video helped you, please like it and subscribe for more tutorials from MathZone African Motives. Thank you for watching.